Hi everyone. I wanted to do something a little different this week. In a very recent episode of the Weekly Space Hangout, we had a conversation about a new method for measuring the expansion rate of the universe. And in this segment of the show, we talked about this new method, but also just what it means for the overall crisis in cosmology. And if you're following this story is just getting more and more exciting as more research is being done. So if you haven't already, you should go to the Weekly Space Hangout channel and sign up. And of course, when we start doing the shows again in the fall, if you want more space news, I think you'll really enjoy it. All right, here's the episode. Cosmology. It's all wrong.
Cosmology and what we don't understand. So this new study is looking at what we call the standard model of cosmology, which is sometimes called the LCDM model. CDM stands for cold dark matter. L stands for lambda, which is a symbol in the general relativity equation that describes the universe as a whole. Lambda is basically the cosmological constant that Einstein first introduced to keep the universe stable, and then became related to dark energy and the Hubble constant. So to understand the model, we really kind of have to know what the value of this lambda is. And if you know the value of the Hubble constant, then you know lambda. Or if you know lambda, you know the Hubble constant. So it all comes down to trying to measure what this Hubble constant is. And the Hubble constant determines the rate at which the universe expands. Basically, the structure in space and time causes the universe to expand at this certain rate that's related to the Hubble constant. And there's several ways that you can measure what that Hubble constant is. The original one is to look at things like Cepheid variables in nearby galaxies and look at their Doppler effects. So they're moving away from us at a certain distance. Their light is redshifted. And then you can use variable stars to find out how far away those galaxies are. Well, this is continued all the way out at ever greater distances to things like supernova. A type 1a supernova is a standard candle. If you know its brightness, you know from its apparent brightness what its actual brightness is. You can find the distance, and then you can measure the redshift, and that's how you find the Hubble constant. It is basically a ratio of distance and redshift. So the supernova way is kind of the way that won the Nobel Prize. It's the way that we kind of think of measuring the expansion of the universe. But there are other ways, and one of them is to look at, say, the cosmic microwave background. So this background heat left over from the Big Bang has little variations in it. And the scale of those variations, as we see them now, depends upon how much the universe has expanded since that initial hot dense state. So if you look at the scale and see where are the most scale of fluctuations, at what size are most fluctuations, you can find out, oh, well, that means that the universe has expanded this much, and then you can find out what the Hubble constant is.
Right.
So that's all fine and good. If the standard model is correct, these two values should give basically the same result. And it's turned out that as we've made ever more precise measurements, they have become ever more in disagreement. So basically, if you look at the cosmic microwave background, it gives a value of about 68 kilometers per second per megaparsec, which means that's the speed at which you're gaining in the expansion for a megaparsec of distance. If you do the supernova measurement, it comes out to about 72. Now, early in the day, their uncertainties overlap, so that wasn't a problem, but we're kind of getting to this where they don't overlap anymore. And of course, what I would always say is what we need are more ways to measure this.
Right.
We need new ways to measure this. Well, it turns out that there is a new way to measure it that's been published, and it uses a completely independent way from the other two. So the way it's done is to use what's known as a astrophysical maser. So more people are familiar with laser, light amplification by stimulated emission of radiation. Maser is microwave amplification by stimulated emission of radiation. It is a microwave laser. and it's emitted by water. Basically, what happens is that when water is orbiting something like a black hole, a supermassive black hole in the center of a galaxy, it gets excited, and it's in just the right configuration that it triggers a cascade. So you get this stimulated emission of water microwaves. And it just happens naturally, whereas here on Earth it happens in a lab. The nice thing about that is that because it's a laser, basically, lasers have a monochromatic color, so they're a single color, and they're very coherent. So they basically emit light at a very precise wavelength.
Right, and so we're seeing a laser, the color is the color of water in microwaves.
Right,
yeah,
basically. So what happens is you can then, because you know that this is water vapor stuff, this is the water maser, you know what that wavelength is. So you can measure the redshift from that galaxy and that supermassive black hole in the center of the galaxy. You measure that really well. So you've got the redshift.
Okay. But I mean, we were already measuring the redshift to galaxies this is what Hubble did, right? To be able to measure the redshift to the Cepheid variables. Is this more accurate than the Cepheid variables?
It is somewhat more accurate, but the real key is that you not only have to have redshift, you also have to have some way of doing distance. And usually distance is things like variable stars or supernovas or things like that. What's nice about this is that this material is orbiting the black hole. So as it's spiraling around, one edge of this accretion disk is coming towards us and is blue shifted a bit relative to the overall redshift. So it's less redshifted, if you say.
Right.
On the other end, it's moving away from us, and so it's redshifted.
Compared to the overall redshift of the entire galaxy. Right.
So basically you get the whole thing is redshifted, and one side is a little bit less redshifted and the other side is a little bit more redshifted. So if you actually look at the signal, what you get is you get a triple peak.
Right.
And it's very easy to identify, but you can make then a very precise measurement of how fast this is rotating at different distances. So that means that this is close to the black hole is moving this fast, out here it's moving this fast, out here it's moving this fast. So you can actually find exactly what the size of that emission is with the lasers.
And you can pinpoint essentially the absolute center of the dead center of every galaxy that you want to look at.
Right. But if you know then what the actual size of that accretion disk is, and you compare it with the apparent size in the sky, you're now using size to measure the distance.
Right.
It's just like looking at a tree. If it's always the same size, you know how far away the tree is because you know how big it is.
Okay, and then you're comparing that with the redshift to make sure the two match up.
Right. Right. And so what you get is you get both size and redshift all from water masers.
Wow. That's incredible.
Completely independent of the Doppler of the galaxy supernovas and completely independent of the cosmic microwave background.
All right. So now we've set up the methodology. And so this sounds like a very accurate way to decide who's the winner. And the winner is?
Neither. The CMB says 68. The supernova method basically centers around 72. This method centers around 75, 76.
Wow.
Could be as high as 78. So it's even higher. It's basically this new result has made everything worse.
So it is not splitting the difference. It's not saying, okay.
It's not splitting the difference, and it's not agreeing with one or the other. It's saying you both are all wrong.
Brian, what's the error bar?
I want to say it's 3.5 on either side. So basically the 72 and this result, the supernova and this result just overlap. They just barely cross, but the best value is way outside of that. So you can say they agree, but yeah, they agree like a freshman physics lab agrees.
Right. So
yeah, I got an overlap. I'm counting it.
So when we consider the distances these are measuring, right? The cosmic microwave background radiation, that's measuring the very beginning of the universe, 13 point, I guess now it doesn't matter. Who knows how far away that is? Not 13.8, some number that could be more or less than 13.8. But then you compare that to the supernova. They're more recent. Where do these masars sit on the time spectrum of the universe?
They're in the same basic range as the supernovas. They're not quite as far, but one of the problems is that because you had the CMB and then you had the supernovas, you could argue, well, maybe it was different over time. The CMB is a really far distance, and the supernovas, although they're billions of light years, are closer.
Yeah.
Well, this new method is in the same range, and so they overlap in distance and they don't agree.
Right.
So there isn't a resolution for them.
Right, but I guess if you've got two methods, both of which are fairly accurate, both of which are attempting to measure the same rough period of time, that seems to lend support to the idea that maybe, we've talked about this again a couple of weeks ago, this idea that maybe it's the Type 1a supernova that in fact we don't understand them as well as we thought we did. Now we understand this, right?
Right, but there was another one that I had actually written about a week before that was a fourth method that was using basically the scale at which galaxies cluster.
Right.
It's called the baryon oscillation. And so what you get is a scale of those. Basically, as the universe expands, galaxies tend to cluster, but the gaps between them get bigger. By looking at the overall scale of that, you now have a measure of the rate of expansion. That one falls that's even closer. So it was even a shorter distance into the galaxy, into the universe. And it was in between the CMB and the supernova one.
Okay.
So it doesn't agree with this either.
Okay. So what's the explanation then?
Wait, there's also another method you can.
Oh,
you can
sure.
use.
Yeah. Fifth.
There's a couple of others. Yeah.
Yeah.
Go ahead.
Wait, you can use so this one was sort of used after the neutron merger discovery with the gravitational waves. Because if you have a kilonova, that gives you can get a redshift from that, and you can get a distance from the gravitational waves. And so if you have the redshift and you have the distance, you can solve for the Hubble parameter that way.
And if we get to more observations at farther away, I know with some of those future observatories, we'll eventually turn up every kilonova explosion in the observable universe. Suddenly you've got a completely independent multi messenger method of calculating. That would probably solve it once and for all, wouldn't it? If you could measure all those kilonovas going off.
What's really happening is that as we're getting more data, it's getting worse. Because it was basically, we're going to have different methods. There's like half a dozen measures of doing this.
Yeah.
And they're all kind of all over the map. And what's happening is we're getting more data, which is great. But what's happening is that all the uncertainties are just getting smaller.
Yeah.
We're not getting this kind of, we were actually supposed to be here.
Yeah.
What we're getting is this. And now not only do they disagree, they now disagree harder, which is really problematic for understanding things.
Okay, so what are the creative ideas that astronomers are coming up with to explain the diverging results?
It starts getting really kind of crazy in the ideas that people are coming up with. So maybe it's axions, maybe dark matter is somehow connected to dark energy. So they're two sides of the same coin, and in the model, they're fouling each other up. It could be that there are, somebody's proposed like quantum fluctuations that would affect the rate of shift from the light. You're basically kind of going into, let's throw out a whole bunch of standard physics and come up with whatever wild idea we can come up with.
I mean, it sounds to me like before the more recent accumulation, like if you just have the two measurements, the one at the beginning and the one at the end, they're different rates, then the answer is, then it's just changing. That it was this rate at the beginning and now the rate is changing now, and there's like some kind of smooth change from the beginning to the end. That's easy-ish to wrap your head around. But the fact that multiple methodologies, which are very accurate, that are measuring the expansion rate of the universe at the same time in kind of different ways, they're not agreeing, and yet they're all very accurate. And so you can't come up with a simple explanation of, oh, it's just that the speed of the universe goes up and down. It's something weirder.
Right. So if the speed of the universe goes up and down in different parts, then the cosmological constant and Einstein's idea is absolutely wrong. You can't have that within relativity.
But Einstein was right. That's something that we always say.
That's one we typically say. But, there could be things like, there could be a fifth force, so what they call quintessence, that is some matter that gives off properties of energy in the same way that dark matter gives off properties of gravity. We see the effects of dark matter from gravity. We could see the effects of this from dark energy.
So then, I mean, if I was to come up with a theory to try to explain this, what little boxes would it need to check?
It would need to, right now, it would need to account for why different measurements, why different methods give dramatically different results. And also, from what we can tell up to this point, why they don't have these dramatically different speeds in different directions.
So it would need to explain. So it would need to explain why masers work differently than supernova explosions, work differently from gravitational waves, work differently from the cosmic microwave background radiation. That isn't it just speeding up and slowing down, because it would literally have to explain each of these observations, why they look the way they do, to come up with a number.
Right. One way to do it is to say you would have to explain why light behaves differently than light.
why light behaves differently than light.
Okay, that one actually broke my brain.
Yeah.
Because microwave lasers are just light.
Yeah.
The redshift should be exactly the same as it would be from the light of galaxies. And we can do those from distinct energy levels, so that should be exactly the same. You can tweak supernovas a bit, but we know that there's a limit to how much you can tweak them.
Right.
The microwave laser optical size is straight out of relativity. So you got to throw relativity out if you're throwing that out.
Right.
The cosmic microwave background is a pretty standard and robust model. So you'd have to throw parts of that out.
Yeah. Could it be dust? Can I just answer this right away and just say that it's dust?
In this case, it can't be.
Oh, because it's usually dust. It's always dust.
Because in this case, not only is the light a single color, it's a single wavelength, it's also coherent. So the scattering takes on a whole different polarization character and stuff that you can account for. So this is a very nice way of measuring cosmic expansion.
Yeah.
And it doesn't rely on a supernova model. You don't have to assume that there's a standard candle, because you're not doing brightness, you're doing size. And the dust, even though it could affect the brightness, won't affect the size. And the size is straight out of gravity. So it's just, this stuff is moving this fast because it's in free fall.
So if you had to place your bets today, what do you like? Or is there just nothing?
It's hard to say what I like, because what I want to see is, I want to see the radical theory.
Yeah.
If it's quintessence, then that means there has to be something, just like dark matter has to be some other particle that isn't part of the standard particle physics model. There has to be something else, whether it's axions or sterile neutrinos or something. Dark energy would have to be something else yet again. It would have to be a whole new thing. That excites me, because it would point us to a direction of radically different physics.
Yeah. Chris, this is in your wheelhouse too. What, place your bets?
I honestly don't know. I think I'm with Brian in the sense that I would love for all the physics to be upended within my lifetime. I'm sure that'd be great for my career. and also because like the implications of this also they trickle into like all of cosmology as well, like how we build how structure forms. It's because it's also dependent on our choice of Hubble parameter and on the choice of dark energy. So if you throw that stuff out, this also has huge implications for how we think like galaxy clusters form, like how galaxies, like the time scales when galaxies form. And so if you pull the card out from the bottom, like the entire house.
Right. And as you say,
I'm glad to be alive. I'm glad to be alive during this time.
That's the thing that I always find so funny is that people always say, oh, astronomers, it's like a religion. They just like, they don't have no reason and they don't want to be challenged in their theories. But you guys are giddy. I would describe you guys as giddy right now at the possibility of exciting new ideas in cosmology and astronomy, and an opportunity to see some fresh ideas. Which is the exact opposite, I think, from what people expect. Dane, I'll give you a chance to weigh in too. Place your bets. Oh, you're muted.
I'm muted. I don't think there are enough data in the Maser thing to rival the huge amounts of data in the other two categories, and so I wouldn't give it as much weight as the other two.
So you think that Einstein was right? You're still right.
I think
yeah.
I'll put my bets on Einstein. Yeah,
it has been a pretty safe bet for a long time, so it does make sense. Fantastic. Well, guys, I really appreciate that. Beth, I don't know. Do you want to have a take as well?
I'm going to stick with Einstein because every time someone sends me some email about Einstein is wrong, I just kind of laugh and go, "Yeah, okay."
Yeah, and mark my words, it's dust. Here are the names of the patrons who support us at the $10 level and more. Want to see your name here, support the work we do? Go to patreon.com/universetoday. Once a week, I gather up all my space news into a single email newsletter and send it out. It's got pictures, brief highlights about the story, and links you can find out more. Go to universetoday.com/newsletter to sign up. And did you know that all of my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes.